You have probably heard of Hubble, based on the Hubble telescope, but more than just a telescope, he's an important astronomer, and much of what he does, or did, related to the age of the universe and the fact that all the galaxies are going away from us. So this video is going to explore what he did and why it is important. Hubble's law is not about other stars, it is about other galaxies. Because all the stars within our galaxy are not necessarily getting that much farther from us. But when looking at other galaxies in the early 1900s, Hubble discovered that if you look at their distance versus their velocity relative to us, he found that it was proportional. That they were getting crazy fast as they got crazy far away from us. And this distance, since it's big distances, is megaparsecs. Clearly, this graph is proportional, so you should know that the relationship is going to be a familiar relationship of Hubble's constant times it. So you got your velocity equal to Hubble's constant times the distance away. If you are given a graph of the displacement of a galaxy away from us versus its recessional or receding velocity, then it's not very difficult to find Hubble's constant because you know it's the slope. And the slope of this line is, I might look out here at about maybe 8,000 kilometers per second divided by a distance of maybe 110 megaparsecs. Maybe I'm going to turn that into 8 times 10 to the third, since it's kilometers, times another 10 to the third meters per second, divided by 110 megaparsecs. And I'm going to get a slope of, I believe that is something like 72 times 10 to the third meters per second per megaparsecs. And I know that's some weird units, but that is a fairly familiar unit for finding Hubble's constant, which we call capital H sub 0. Based on that equation, which we have from our graph before, we can make a calculation of how old the universe might be. So let's say that we have the most distant galaxy that we can see with the most powerful telescope. That is going to be the farthest value d possible, and it's been traveling at the very high speed v away from us. If we rearrange this and set velocity over distance equal to Hubble's constant, we know from before that velocity is, or from basic physics, is distance over time. And if we rearrange this to say that velocity over distance is equal to 1 over the longest time we can have, if this is the farthest distance away, we can say that this is true. So we can substitute in for velocity over time. Put 1 over t is equal to h over 0. And we can then say that time, age of the universe, is equal to 1 over Hubble's constant. So, based on what we said in the last screen, is that the age of the universe is 1 over the Hubble's constant. And so the age of the universe is in the most awkward form possible, with megaparsecs per 74 times 10 to the third meters per second. This is going to be an exercise in unit conversion skills. See if you can convert that into years. Pause it, see what you can do. I might have gotten a little bit dumber when I did this, but it does work out. Convert your megaparsecs to a million parsecs, and then the conversion of parsecs into light years, so light year, and the conversion of light years into meters, which is in your IB data booklet, 10 to the 15th meters, and you are going to end up with something like, oh, everything cancels, and you end up with a massive amount of seconds, 4.28 times 10 to the 17th, I believe, seconds. You're most of the way there. And then it is just a matter of taking your time in seconds and doing the simple, hopefully simple, conversion to years. And you can say that that's 13.6 times 10 to the 9th years, or about 13.6 billions of years. And that's old. It's older than me.